Hello, my name is Thomas. Today we are going to talk about Proposition 5 of Leibniz's on the arithmetic quadrature of the circle, the parabola and the hyperbola. And for those who did not do so, I recommend watching the earlier videos on Proposition 2 through 4, and this way you will get familiar with the nomenclature and the things I'm talking about here. So let's start right away. As in the earlier Proposition 4, we have these three little sliders which should represent the element of a series containing those three elements. And we said in Proposition 4 that the difference between the outer quantities A and E, which we call F, is never going to be larger than the sum of all differences within the series. In this case of the three element series, there are going to be, of course, two differences, namely the first one being called B, which is the difference between element A and C, and the difference D, which is the difference between the quantity of elements C and E. And again, in the previous Proposition 4, we found out that the difference A and E, which we called F, is never larger than the sum of B and D. And that's what we're going to show now. So I raise the quantity of the element A to some value, and you see, as I said, Leibniz in this proposition added another degree to the whole thing by saying that if there is a quantity G which exceeds the true difference B by some amount, in our case we chose to be the amount 1, and if there be another quantity H which exceeds the true difference D by 1, it is of course also the case that the sum of G and H, this one here, is never going to be smaller than the difference of the outer quantities. And this is what we're going to show. So I have a series of natural order here, because all the elements, if you succeed like step by step through the series from element to element, the quantities always are going to decrease. Otherwise, if you do it the other way around, you also have a natural order if the quantities only ascend, like this. And you see, in this case, the sum of G plus H, which are the true differences B and D, exceeded by 1. They're of course going to exceed the outer difference of A and E by a number of 2, because the degree of excess, as we call it here, applies to the true differences B and D. So it's of course the case that the sum of G and H exceeds the difference between the outer elements by a number of 2. 1 from this side and another 1 from this side, making it 2. Because in Proposition 4 we found that in a case of a natural order like this one, where from element to element you only increase quantity, or you only, like this, decrease quantity, the difference is always going to be 2. And without this degree of excess, these numbers are going to be equal. So this seems logical. For those who have watched Proposition 4, this should be no problem of conceiving. So now let's do a disturbed order series. Disturbed order series, as you may know, is called, or Leibniz called a series where you have an descension, for instance, and an ascension in the same series when you go step by step from element to element. So it may at the first section go down and then go up again, and that's a disturbed order. A disturbed order would also be one like this. Yeah. In this case you have the ascension of quantities in the first section, and then a descension in quantity in the second step. And this is the condition of it being a disturbed order, that you have both an ascension and a descension within the same series. In what order, that does not matter. But as you see, the same principle applies as in Proposition 4. As soon as I am in the range of a disturbed order, I tend to move the middle element, being C, away from both the outer elements, which is of course making the sum of the differences always very large, because this difference is going to increase for both of them. Whereas when I'm in a range of the natural order, meaning my middle element is in between the values of the outer elements, then, and if I move around in this range, the sum of all differences, and additionally plus the degree of excess for both these true differences, is not going to change. It's only changing when I exceed one, or when I exceed, or when I am less than the one of the outer quantities. So now I'm less than quantity E. I move away from both, and the sum of difference increases. Or when I'm larger than quantity E, then it increases. And of course, this is also true if you just add another, in this case 1, to both the true differences, getting G and H. And the same rule applies, just as in Proposition 4, to Proposition 5. That was what he wanted to show, and it's playing also a role in a later proposition, as I already mentioned before, where Leibniz uses this rules to conduct a proof on the equality of certain types of constructed areas within Proposition 6 and Proposition 7. So that's all for now. And if you're more interested in these things, I really recommend you watching Proposition 2 through Proposition 5. Those are the propositions dealing with all these series issues, and these propositions are laying the basis for the proof that's coming up later. So I hope you enjoyed it, and stay around for the next propositions coming up. Thank you very much, and bye-bye.